congrats for meeting it this month. Yeah, so yeah, we will first continue the problems discussion for this context of the first 4 days, and then yeah, hopefully we still have time for the special topics that I mentioned, but hopefully we have time. Yeah, so let's continue. So yesterday we talked about this contest day 7, and we discussed the four tasks. So we will next discuss maybe 2 or 3 more from this day, because this is a hard contest. So maybe we start with problem I, one of them. Is there any volunteers that want to discuss this problem? Okay, yeah, so this problem, yeah, this problem is about, basically it looks like a complex health problem where there's a race where the ith person have a speed, and then at a given time they may change the speed. Yeah, so, and then there are also, whenever there is a speed change, you also have to vary who is the last contestant, right? So, yeah, but the way that I solve this is, so actually notice that the speed of the participants can only decrease. So that means actually, if we have several lines, let's say this contestant, the speed changes to this, we don't actually need to remove this line, because yeah, even if we don't remove this line, starting from here, this line will not be optimal, because it's always written by the new line, the new speed, right? So we can actually read the query offline and then add all the lines first, and then we can solve all the queries offline for each position, right? So now the question becomes, we have already all the lines, and we want to solve this, right? But yeah, I can't figure out how to use convex here, because first of all, the constraint is quite huge. So if you try to compare two floating point, like let's say, yeah, multiplying this might be tricky. You need some data structure data type that can handle very big integer. But the other issue is that, because in case of ties, we need to report the contestant ID having the contestant having the lowest ID. So if there is like several lines like ties, it's very hard to decide which line you have to pop from the stack and so on. So it's actually not so easy, even though the problem seems to be standard convex hull, but handling the ties actually is not so easy. So the way we can solve this is actually using divide and conquer technique. So yeah, if we already have the lines, if we sort the lines by gradient, then we know that even without removing the obsolete lines and so on, we just keep all the lines. So even though some of them might be like obsoleted by, let's say, like usually if there is this line and there is this line, there is this line and there is, let's say, this line, right? This is the minimum line. So usually we remove this line, this. Usually we remove, let's say there is this line, we usually remove the line. But for now, let's just keep it there. We don't remove any lines. But once we sort by gradient, we know that, so this is the first line, this is the second line, this is the third line. Once we sort by gradient, we know that the answer for each query can only increase, like the optimal line for each query can only increase. So yeah, we can actually use a divide and conquer technique here, where we solve the middle query, and then yeah, find which line is optimal using linear naive search, and then try to solve for this. So actually for this kind of convex hull queries, if the lines are given beforehand, you can also use this. Of course, for some problems, usually like, especially like DP problems, you cannot do this, because like the standard DP, something like DPJ plus something that requires JCJ, CI, something like that. You cannot do this because, like, usually the lines are added in online fashion. Like, so you add lines, and then you need to query for the next DP, and then there's a new line, and then you add, you query the next line, and so on. So yeah, but if the lines are given beforehand like this, and yeah, the nice thing here is that if the contestant reduces speed, you can just add a new line without removing the previous line, because it's never optimal to use the previous line. Right? So yeah, this is how you solve with defined compler, and it's in this way it's very easy to handle the ties. So yeah, I'm actually curious. Those people, I think I randomly opened some of the 7 submissions that I got AC, but I think all of them are using Lichao or some convex cell that I don't know how it works. So if any of you want to present your solution, it's actually good. Any takers? Yeah, okay.
Okay, so basically, the biggest difficulty in the convex full quick was like if I had some different function that had the same value. So I had two different the biggest ones. So what I did was basically a pair with the line here. I'm sorry, the result here when I check the Lichao quick, right?
Okay.
And I need the index. I will maximize this index. And to do so, I basically did in each index I have a line, okay, and I have a queue. And in this queue, basically, I have all the index that contains a line at this point. So it is like a stack of priority queue. I don't remember really. And I just get the highest index and check if this index really is this line, because it can be changed. Maybe it changes. Then I get this value. I put into the index, and when I return, I also get the largest index by this way. Because that's the biggest difficulty, getting the index, not the value.
Yeah. And you also don't remove the lines, right? Like you just also do the same thing. Yeah, because removing a line in this kind of data structure turns out to be quite difficult. So, but yeah, for this problem, fortunately, the speed cannot increase; it can only decrease. So we don't actually need to remove the line. Yeah. Okay, next, boxes. Any volunteers? Who solves it? And who will try to present? Okay, maybe I can just do it. So this problem, so you are given a boxes of several weights, right? N boxes, several weights, and then you also have a big box with the width. Sorry, not weight, width. And then you also have a big box of width W, and then you want to put these boxes into this big box, such that of course the sum of this W is not greater than this, and you want to find how many configurations, right? And then here we only care about the orders. So not only care, but here we care about the orders. So like if you put W1 first and W2, this is two different solutions, assuming these two weights are different. But if they are the same, this is the same, right? So boxes with the same width, we consider them the same. And what makes this problem difficult is that there is another constraint that says that if once you put them, if there is still a remaining box that can still fit, the solution does not valid. The solution does not count up, right? That's the difficult part of this problem, because otherwise we can get a simple DP. I think the constraint is quite small.
It's 100, and this is 100, and W is 1000.
Yeah, okay, yeah. So Yeah, usually if we consider these boxes to be the same, if they have the same width, we don't do like a DP of like I where we only consider the last I boxes. We don't do this because otherwise, yeah, it's hard to maintain like, oh, this width have already been before, and then we have to consider them. So this is how you do this. Instead, you create like an array of 0 to W, and then for each you actually store how many boxes are there of that width, right? So let's say the input is like 1, 1, 2, 5, 2. Then here you have 2, you have 2, you have 5, right? So this stores how many boxes have that width, right? Okay, and then the DP is like we only want to store boxes of width 2 and width 5, something like that, right? And then and then we can have a DP of which prefix we want to consider. Like the minimum weight basically of the boxes that we can put now, and then how many boxes we have put so far. Put, and then the remaining width, right? The remaining width of the large box that we can that still fits, right? So and for this basically, right? Let's say we want to compute dp to x w, yeah. Let's say, and we basically want to look how many boxes we want to put that has width 2. So it's something like the sum of 0 I 0 I like how many boxes are there with weight 2, something like that. Okay, and then you of course do see dp w min plus 1. How many boxes we have put is this x plus I, and then remaining width is w minus I times 2, right? Okay, and then you times something because let's say we have already put x boxes and we want to put another 2 boxes, another I boxes, let's say. Then there is then this you have multiplied by x plus I choose x, right? Okay, so this is the standard DP if there is no condition that like the one that I told you earlier, like there's no condition that you have to, the box must be like full, like you must not, yeah. But there is that condition that if there is a remaining box that still fits, then it's not counted, right? So the way to handle this is that you can actually modify the DP. Let me make sure I'm still remembering this one. So you can modify the DP to have an extra parameter where this is a boolean, and this boolean tells you whether you are not allowed to take all of these boxes. So you have to I think you have to do like the other way around. I think you instead of doing that, the DP is like the prefix. So this is instead of W min, this is W max, and then this is minus 1. Okay, and then but then the DP is like there is another condition of the DP where from this you cannot take all of them. And then you have and then from here there is this sum. So it's getting a bit complicated, but basically the DP is now let's say you consider this, and then you also want to check whether so this is W max here currently. So this is still the same. And then we want to plus the case where we only want to take some of this, but take all of this. Right? So yeah, and then we can check whether that is valid by checking whether W, the remaining width, minus sum of all this W, like sum of the smaller W, minus whatever you want to take here, must be smaller than this weight. Because otherwise then this weight can still fit in, right? So yeah, that's how you do it. Is it clear enough? Yeah, so that, yeah, the DP becomes slightly complicated, but yeah, you can solve it using that solution. So yeah. So it's something like sigma 0 I, and now this must be strictly less than CNT2. Yeah, and then yeah, do what I just mentioned. But first you must check whether if you take I copies of this and then take every boxes here, the remaining gap must be smaller than this weight. Yeah, and then you can do that. You can take some of this and then all of this. Yeah, and then of course this DP still remains where you take several of this and then you take not all of this. That still remains. Yeah, something like that. Okay. Yeah, maybe let's do one more for this day. Rubinas, any from you? I think we can do this problem quite a bit quicker. So the idea is that the problem is you are given a tree, and then it's a standard like it's a standard of like for each node you want to bring the message to a root, but then each person has a different speed, and you can choose to switch here, and then it has a different speed and so on, right? That's the problem, right? Yeah. So it's actually quite similar with problem B, except that now it goes to the root instead of to the leaf, right? So the standard convex hull can work, but now the problem is that yeah, now we can actually solve it with like you DFS. So you do like, let's say you choose a path first, and then when you are here, you compute the DP and then insert a line, and then do the same thing here. But then when you go back up, you need to somehow remove this line, right? So this is the tricky part. And of course, when you climb back here, you have to remove this line. So yeah, actually there is a way to make this work. So let's say the usual stack, of lines. Okay. So let's say this is the lines, like of increasing gradient, right? Yeah. And then let's say you want to insert this line here, like the dpj, and then m equals fj, c equals dpj, or something like that, right? And then yeah, inserting this line might pop the stack, right? But what you can do here is that you do the pop, and then you override this value. But when you override this value, so you keep this stack actually, you don't actually pop them, but you have a pointer of which one is the head, and the array is, yeah, it's just, so when you pop the stack, you just increment the head, you just keep the value. When you override, you keep the information of what is the original line that you pop here, that you override here. And then when you climb back, you actually change it back. And then you change the head back to here as well. So yeah, that works actually. So yeah, so basically whenever you are popping the stack, and then replace, like let's say you pop all the way here, and then you want to replace this with this line, you first, before you replace, you save what is the line that you override, and then when it goes back up, yeah, you change it back. So yeah, and then the rest of the lines still correct as well. Yeah, and then you, of course, so you keep the values of what's the line that you override and what's the previous values of the head. Yeah. So yeah, this can solve problem K by having to like undo inserting a line. Yeah. When you climb back up. Okay. Any questions? Okay. Yeah, maybe yeah, let's maybe move to the next one. Or maybe I can just mention quickly, jumping stones is a data structures problem. Basically we want to find out, there's a query L to R, and we want to find out if the like consecutive ones are squared, what's the sum, right? That's a, yeah, you can just use a standard data structure. Yeah, but each node you have to calculate like what's the, of course, what's the answer in this range, like all the square here. But you also have to count the, what is the max, like prefix, suffix, the ones here, like what's the longest suffix that is 1, and then what's the longest prefix that is 1. And then when you merge them, you have to count this as well. So you have to, yeah, you have to, of course, add the answer from here, add the answer from here, and also add this square, right? And then you have to minus this square and minus this square, because you want to remove this square and this square. Yeah, so it's actually just a standard segment tree, but how you what the values inside the node are, yeah, you just think about what you need, and yeah, because if you just start the answer, when you merge them, you can just take the sum of the answer, but you need to also count the ones that are cut in between these two nodes, right? So you also need to store the prefix and the suffix. Yeah, so that's for problem L. Okay, let's continue to the next day. But any questions before that? Okay. Yeah, let's continue to the next day, and yeah, this context is a bit easy side, but the first two problems are quite hard. So yeah, so any focus for, let's do the instruction and then ground first. Sure.
Okay. So in the problem, you have the Cartesian plane, and initially a point at 0, 0, and some checkpoints. And for each checkpoint, you knew that at some time, the point was at this coordinate, and the point moves across the plane. And the way the point moves is in one of the 4 directions, right? We're also given a list of instructions, of directions, and we want to count how many permutations of those are consistent with all the checkpoints, right? So the idea is the following. You know that between one checkpoint and the next one, there's some time span, and there's also some difference in x and difference in y. The difference in x tells you that necessarily, for example, if this one is 10 to the right, then you know there has to be 10 east in this section of time, right? And if it's 10 up, you know there has to be 10 north in that section, right? And if the time difference between these two checkpoints is exactly that, 10 plus 10, then the only possibility is some permutation of that, right? But if the time difference is more, then you can add some useless instructions, for example, go north and then south, and then, or go east and go west, so that the time matches up, right? And these are the only two possibilities that you can do. So the idea is to store an array with how many different possibilities are for this range, given that we add I of this side. Because if we know how many we add of this side, we automatically know how many we add of this side, right? And the way that can be calculated is just, you know how many east and north are we are required to put there. Then we iterate over how many extra we're putting for each I, and then we just do the combination. If we have A north, B east, C south, and D west, then the number of possible combinations is the sum factorial over the sum of the factorials, the product of the factorials. Right? So this is what we put in the array. We start with the required movements, and then we add some amount of this one and the rest of this one. Okay. So that's for one time interval. And then for many time intervals, what we can do is, like if we wanted to concatenate two intervals like this, and we want to do something that works for this whole thing, with certain number of, for example, with I of these movements, they have to choose some A here and some B here that add up to I, and then choose the 8th element in the array and the 5th element in the array, right? Because if we want to put I of these in total, we have to divide them up and put A here and B here, right? So we have to iterate over all pair of elements that sum up to I, multiply them because we have to, it's any valid solution for here and any valid solution here, then add them up. So that's a convolution, right? So we need to take two consecutive ones, or not even consecutive ones, and do the convolution. And once we have the convolution for the whole thing, we just need to know how many we actually need to put. Because in the original array, like we take away all the ones we were forced to put, and there's some of these left and some of these left, and we count how many of these there are. We just index the final convolution, and that's the answer. And to do the convolution, we use FFT, so n log n, but we have to convolve many different arrays. So what we do is we always take the two smallest ones, and we convolve them together, and we put them back into the bag, and so on until there's only one element in the bag, and that amortizes to n log square. Any questions?
Yeah, okay. Yeah, exactly. So yeah, you basically need to multiply to like sequence of like number of possibilities here, and then yeah, basically for each, basically yeah, to like array of possibilities, you want to combine them. You have to convolute like look from A to I, A times the I minus A, and then this is where you use the type FFT or number theoretic, entity. Yeah, so yeah, that's how you solve. And then yeah, we have to combine n n of them. So yeah, if we do convolute this and this, and then this and this and this, it might be n squared, because once you convolute several of them, it might get large. No, actually that's not how you say it. Like, because the initial array might be large, and then might be small, but then if you do this, it will be n squared, right? Because this array will cost several times, like n times, right? Okay. Yeah. So you do from you always choose the two smallest, and then you convolute them and put it back, and then again do it again. You take the two smallest one and then convolute them. Yeah, so that works. Okay, so next is problem I, forming compounds.
for this problem, we have like n type of atoms, and then each type of atom has some weight, Wi, and you wanted to pair the type of atoms, let's say the types A and J, and you will assign some value to the pair, that is the number of pairs X, Y, that satisfies WA times X plus WJ times Y less or equal to 10 to the power 4. And you wanted that X and Y be integers and be positive. And then you have all the pairs of possible, all the possible combination of two type of atoms, and then you put them in a bag to the pair of atoms that have the same value. And then you wanted to answer some queries of basically an abstract problem type. So we have like two different problems. The first one is the abstract type, and then this problem basically is just a theorem well known, that is the chicken magnet. That it tells you that basically I did it with Wy and Wj co-primed because you can divide it by the GCD, but it basically tells you that up to the point of the LCM of Wy and Wj, plus 1, all the values can be reached, and for the values less than the LCM, then only Wi minus 1 times Wj minus 1 over 2 are reached. So we can compute the value of the pair, and then for the next problem we just can do a FFT approach that it will take, like Charles said, n log square. Doing taking the two vectors of less size and combine them. Any question?
Can you repeat the FFT approach?
So the idea is the next one. Let's say you have that you have the size of the bags of the pairs. For example, you have 4, 7, and 9. Then what will you do is you take the next polynomial, that is x to the 1 plus x to the power 4 plus 1 plus x to the power 7. So after multiplying this, it will give you some polynomial, and the exponent of each x is a value that you can reach by doing abstract. Questions?
Okay, thank you. Yeah, so basically this problem is like kind of split into two parts. First is like the number theory part, and then the second one is the DT problem. I need to check something. Consensus is slow today. Okay. Yeah. So basically for the first part, it's exactly what you say. You want to make sure that Wi and Wj is co-prime. If it's not, then you know that the numbers that can be formed with this are actually a multiples of the GCD. So you can actually just take 10 to the power of 12 divided by GCD, Wi, Wj. And then this is the maximum now becomes this. And then you solve, and then you divide the Wi by the GCD, Wj by the GCD, and then it's the same problem, right? So basically you like normalize so that the GCD of WI and WJ is 1, and then yeah, you use this formula to get how many numbers are you can make in numbers smaller than this, and then of course you take the, and then plus the 10 to the power 12 minus the LCM, something like that. That's the larger greater than LCM that you can make, of course, until the bound, and if the GCD is not 1, then take this M minus the LCM. And then the second part, actually there's another solution other than using FFT. So the other part of the problem is now you are given several numbers, this n numbers, or n squared in this case actually, if the n is the number of atoms. But okay, let's just say n. But when I say n, it's n squared to the source of to the original problem. Or let's not use n then. Let's use what? K numbers. Okay. And the sum of them is up to k as well, right? Yeah, and we want to find for each 0 to k whether there is a subset of them that sums up to k, right? So of course there's a dp k square where yeah, standard dp like which number we are and what's the current sum, blah blah. But since the sum of them is at most k, we also have like k square root at log. We also have this solution. Yeah, so we also have this solution by taking for each number, like let's say you mentioned 479 just now. Let's group all of the same number together and count the number of occurrence, right? So let's say, yeah, if 1 appears multiple times, then we have like 1, 3, 4, 1, 7, 1, 9, 1, right? And we know that the number of distinct elements here can be square root of k, right? Because in the worst case it's 1, 2, 3, 4, but yeah, the sum can be at most square root of k. Now the question becomes, we want to take, for each of this, we want to take some copies of this at most to the number of occurrence, right? Make sense? Up to this point, and we can actually, yeah, this is a standard like knapsack problem where if you are given like, okay, in knapsack there is a 0-1 knapsack where for each item you either take or not take, or there's also like an infinite copies of each item, right? But if there is a like limited number of items per limited copies of each item, you can actually solve it by doing something like this. So let's say there is a phi 2 weight 4, and then the number of copies is 10. Then you can make you can duplicate this item by saying phi equals to, like by making copies that are this many copies. So like you duplicate this item into like phi 2 w, let's not use 4, 5, and then phi equals 4, w equals 10, equals 8, w equals 20, phi equals 6, w equals 8, right? Because any numbers between 0 to 10 can be achieved by any subset of this, right? If this is, like, let's say 11, then any numbers between 0 and 11 can be achieved using this, any subset of this. So you can create 4 items where each of the items is basically taking like 1 copies, 2 copies, 4 copies, or 4 copies, right? So with this, you can, each of these items can be duplicated at most log of this, right? So you get k square root of k log k solution, and you don't need FFT, right? And yeah, that's what I want to check whether this passes, because it's quite tight. Like it becomes 500 cubed times, because this is 500 cubed, and then times log. But I think it passes. This is the solution that I coded, that I have in Polygon. There is also another optimization where you can remove this log. So actually, this knapsack can be done in linearly as well without the log, by using like a sliding window. So yeah, basically, if value is 2, weight is 5, then the dp is like, yeah, you only take, okay, let's just say weight is 1 first, for simplicity. Okay. Then we can keep a sliding window of a number of copies. Right. Let's say copies is 5. So we can keep a sliding window of 5 here. And then from here, we can take whether there is a 1 here, like the if this is a, yeah, if we want to check whether we can make this copy, then it's just, if there's a 1 here, we want 1 here, right, instead of maximizing the value, right? Yeah, so, and then when we want to compute this, we move the window here, and then check whether there's a 1 value here, right? Yeah, and then, something like, but yeah, it's something like this. And then if the, okay, something might be wrong with this. I kind of forgot the detail. But yeah, you can do this linearly as well. So there's a k square root of k solution as well. Yeah. Okay. Question?
Can you send us this not without the linear solution without the log? Not linear, right? But can you send this solution afterwards? Because I'm interested in.
Okay, so which one? The k square root k log k or the k square root of k?
The k square root k
Without the log. Okay, I'll dig it up. Yeah, I think yeah. If I can figure it out, I'll send it to you. I'll let you know. Yeah. Yeah. So yeah, this becomes n cube, right? 500 cube. Which fits the time limit. Yeah. Okay, and then next, I think we can just go through this quickly for project team. So, yeah, project team basically the question is like, if I remember, the question is like there's a query, each query is 4 integers, and then the question is from there is like an array. And then we can only take from L to R, the element from L to R, and the element that is between L and R. And the question is, oh, there's S as well, right?
Yes.
Yeah. And we want to. The question is how many elements you can take so that the average is at least S, right? Yeah. Of course, the observation here is that we want to take the largest element that we can. So we basically, yeah, and then we can do binary search, or maybe not necessarily binary search. Yeah, probably not necessary. But yeah, we want to find the largest y, such that the largest y element in that satisfies this and this divided by y is greater than x, right? And we can vary such because if we, yeah, basically the monotonic property is achieved. Like if we cannot take this many elements, we cannot take more elements because the elements that we're going to take is even lower, and the average will go down, right? So yeah, and then yeah, once we fix the value of y. This is just a persistent segment tree problem where if we have the segment tree, the leaf is the values, right? And then we build each segment tree from 1 to L and 1 to R, 1 to R. Then we can get what's the sum of the y what the sum of the y largest value that is still smaller than R. Yeah. So we can solve this using persistent segment tree. Yeah.
Someone passed this problem with n log squared, with like binary search on the with 2 binary searches, one binary search and another carry in segment tree. I'll talk to you later.
Wasn't us, but someone said that they did test it.
Oh, okay.
yeah, I don't think you need binary search. Yeah, you can do n log n. But I think n log square n should pass. I think I have a solution based n log square n. But you can do the optimization where when you traverse the segment tree, you know which way to go, left or right. Yeah, like doing the usual technique. Yeah, polygon is very slow today. I don't know why. I want to check my solution whether it's log square or. I think I have some that is log square, I have some that is log n, and the log square passes as well, but it's very slow. I cannot check right now. Okay. Slow. Yeah, we have a log square solution here, and it runs in it runs in so slow. And the time delay is 5 seconds, right? So that's it. You can just it runs in 1.7 seconds. Our solution that uses log square. Yeah.
You were able to pass with n log squared?
Yeah. In 1.7 seconds.
Can I take a look at
Yeah.
your code after?
Yeah, there's a binary search here. Oh wait, this is long. Never mind. Sorry. Yeah, sorry, this is long. Sorry.
What's the story optimization?
Sorry?
The story optimization.
This one.
You have mentioned over story. The story
Oh.
optimization. Okay.
Okay, so yeah, maybe log square. Yeah. Okay, let's just continue anyway. Okay, yeah. Problem E is a construction problem where, it doesn't require any techniques there. It's just creativity question whether you can get the construction or not. Yeah, maybe quickly, anyone wants to share their construction? Yeah, sure.
Hope I can remember it. Sure. So we have two main cases, like when it was odd. So I don't know, let's do 5.
It was prime number, so
It was,
it was prime number.
oh, we didn't check that. Okay, so maybe we did one, but wasn't necessarily one. So we just placed n here, and we just kind of compensated all around since we could start playing with this. The only thing we had to do was do this kind of opposite sum. And then for everything missing, we can just put a 1. And with 7, it would be like the same. So we can do 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we need to put a 7 there. 3 and 4, 4 and 3. And then we could just play with that. Missing pieces. And that works. We actually we didn't know the prime for it, so we also found that it was possible with every even number over 8. So we also have one. It's basically like instead of this one we use the 4 middle squares. So that's why you need at least 8 because you need like this 4 in the middle to kind of simulate this. But it still worked. And by brute force we found that we demonstrated that it wasn't possible with 3. And by brute force we demonstrated that it wasn't possible with 6. So yeah, that's basically like this.
Yeah, so prime number so must be odd other than 2 and 2 and 3 you can write a brute force. 2 will help you because it's on the sample. 3, yeah, you can write a brute force, or it's actually quite easy to see why it's impossible as well. Like you can play around writing, and then yeah, it's impossible. So yeah, that's the solution. Okay. So any questions before we move on? I think we can move on to the next stage. Yeah. Sorry? No. We move on to the next stage. Yeah. So next, this is because we try to move on because there are some hard problems on this day. We might need to discuss. I think there's an obvious cut there. The 6 top has less than 10 solvers. So we're going to discuss that. I think let's do it differently this time. Let's do from K, because the upper one are a bit hard, and yeah, finally I got a problem that none of you can solve. Sorry. Problem K. Any volunteers? Yeah, sure. Okay. Problem K, 3 beauties. Yeah, sure.
Okay, so in this problem, we had a tree initially with zeros at every node. And there were updates of the form, you were given a node, and to that node you increase the sum by some number y. Then for all its children you increase it by y over k, floor. And for all its children, like this one as well. And for all their children it's y over k squared. And so on, right? At some point, yeah. And then there were queries of what is the sum of some subarray. Okay. So this problem has 2 main cases where k is given for each update. Has 2 main cases when k is 1 and when k isn't 1. When k is not 1, what happens is that this becomes 0 very fast. So you only need to consider a very small number of levels. When it's 1, you add to the whole subarray, you add y. So yeah, those are the 2 cases we have to consider. So what I did is the following. For the case where k is 1, you need to, for example, imagine there's a query that adds 1 to all the subarray. So first, we need to calculate what's the size of the subtree. In this case, the subtree is 6 numbers, right? So we annotate here that that the sum of this subtree is plus 6. Okay. And also for any nodes that have this as a child, the subtree also increases by 6, right? So we need to when we do the query, we need to know the sum for all the children of this number, this plus 6. But there's another case, for example, if there's a query here, then the update that came here that was to increase the size by 1 of all the subtree also affects this tree, right?
Sorry, you mean 6 times y, right?
Yeah, if we increase all the subtree by 1.
No, the y, 6 times y.
Yeah, but I'm doing an example where y.
Oh, okay.
If we increase the whole subtree by 1, then this increases by 6. But for example, and all the parents of this node also increase by 6, the query. But this node, for example, only increases by 2, right? So I handle those two cases separately. We annotate a plus 6 in this node. And then when we do the query, we need to know if the sum of the y's for all the parent nodes. Like for example, in this node, we also annotate that y was 1. So when we do a query of the node, we need to do the sum over all the subtree of this value, and then the sum to the root of this value. Okay. And with those two numbers and the size of the subtree, we can calculate the answer for k is equal to 1. And the way I did this was with an Euler tour. Like we can go through the tree in DFS order, and we have an array. And for example, if we need to when we add 6 to this number, we can add 6 to an element of the array. And then when we need to query the whole subtree, it's always a range. All subtrees are ranges in the Euler tour. And then when we need to, we have a separate array. And when we need to say that y is 1 here, we actually, what we do is take the whole array corresponding to this tree and add 1 to the whole array, right? And then when we query this node, it's going to fall within this array, so it's going to have that plus 1 that we needed, right? So yeah, that's what we did. And then for when k is not 1, we use at most log levels, right? And we still calculate what the change of value of the node of the root node is. That change we can calculate by knowing for each level how many children there are, but only a few levels, only log levels are needed. Okay, so we know that the change in the value of the subtree of a node, that the sum plus something, which we also add to the first array. But then when we do a query, all the updates that were within the subtree are already handled by that, but the updates that were done in nodes on the path to the root are not handled, right? So what we do is we iterate, like for example, imagine there's a query in this node, we have a path. We need to add to the value of the query we calculated all the updates that happened on the path to the root, but up to log levels again, right? And for each of those updates, we need to figure out how much it changed our sum. And you know that this updated at most log levels. So we iterate all the levels that are below this node, and for each of those levels, we know how many. We know what the extra sum was, and we know the size of the level because we keep the sizes of the level in each node, and we just need to multiply those. And this ends up being log square because we iterate all the log parents, and for each parent, we iterate log levels below. So yeah, the query ends up being in log square.
How do you get the number of descendants that are ith level?
You just start with all zeros, and for each node we go log up, and for each parent we add 1 to the corresponding node.
Oh.
So it's a pre-processing stage. Any questions?
Okay, yeah. Yeah, this is also the intended solution, dividing k equals 1 and k greater than 1, because, yeah, as you mentioned, for k greater than 1, the update can only be limited by number of log levels. But for k is 1, yeah, for k equals 1, actually there's another solution with just, if you already do the Euler term, and then you want to update all the values of this subtree by y, then you just do a standard plus y, where you plus y everything of this using lazy propagation, and then and then there's a query, just another query, right? What's the sum of this and this? So yeah, it's just range sum query, but that can be updated in the terms of from L to R, all increased by y. Yeah, that's lazy propagation technique. So yeah, that's for k equals to 1, there's one solution, that solution as well, and then for k greater than 1. Yeah. Basically, this log square solution. Yeah, basically you, like, for each, just mention, for each subtree, if there's an update, you count how many failure of this increases in the subtree, and then, but then that doesn't cover, like, so that covers if the query is outside the subtree, but that doesn't cover well if the query is inside the subtree. So when the query is inside the subtree, you actually climb up. Yeah. So because you know that if the query is too many levels down to this subtree, that won't change actually the answer. So the only updates that can change the answer is only several levels up, or all the subtree. But all the subtree we already counted already during the update. So that is fine. So that's for problem K. Then next is problem J. Yeah.
Okay, so problem J was we had an array and several queries. For each query would have a range, and what we're asked to do is answer whether if we took the values from this range, like we have a bunch of values here, if we were to sort them, we want to know if they would form an arithmetic progression, right? So what we do here is we first check if there is some repeated item value in the range. If there is, then the range should be all equal, so you can like solve this case separately. And to do this, you just keep like a pointer. If you have like a 2 here and 2 here, we keep a pointer to the next value, and then we just take the maximum. Oh, we also have updates, right? Yeah. But we keep the pointers here to the next position of the same value, and we take the maximum in the range that it should be smaller than R. So this way we can check if they are different or there is some repeated element, and we treat this case separately.
The minimum, right?
The minimum, yeah.
Minimum next value.
Yeah, sorry. So yeah, and this is easy to update, right? You just need to like start a set of occurrences, etc. So the other case is when everyone's different, we want to know if they would form an arithmetic progression. So the trick here is to note like if we have like the minimum and the maximum value in the range, then we know what the difference should be in the arithmetic progression. It should be like the difference divided by the number of elements minus 1 that we have. So what you need to check is whether all the values, when you take, they should have the same congruence modulo this difference. So one way we could do this that is not good but would work is if we took all possible and choose two value possible indices here and take their difference and take the GCD of everything, it should be exactly equal to D because of the congruous thing. It's not hard to to convince yourself of that, but we can take, obviously we can take like all n squared and choose two possible differences here. But there's a trick here. If we imagine like all these values in a graph, so in each node you have the value for each position in the array, and like if you have like x here and y here, you would put this on the edge. What we wanted to do, we would like to do is take all of the edges and take the GCD. But there's a trick here. Using Euclid's, you can convince yourself that actually any spanning tree of this graph is enough to get the value of the GCD. So what you do is you build a simple segment tree that would store minimum, maximum, and the GCD of some spanning tree of the values in the segment. And when you want to combine the two sides, like minimum and maximum is trivial, and you just take like the GCD of the root. This is supposed to be G. It's the GCD of what? The GCD on the left, GL, the GCD on the right, and the GCD of any element here and any element here. You can take like the minimum here, the minimum on the left, and the minimum on the right. And this works. So just check this GCD for the range. If it is equal to D, then yes, otherwise no.
Mine is on the GCD of the...
Yeah. Any questions? You can also solve this with hashing. Some people do like that. You can like assign for each value like x, some base to the power of the value, and we can compute what should be the hash if it was an arithmetic progression using sum of geometric progression and do like that.
So basically what you mentioned. The GCD actually you can also just consider consecutive values, the GCD of the difference of the consecutive values. So basically, this is the query. You can just take the GCD of this minus this, this minus this, and this minus this, and the GCD of this should be equal to the D. You need to keep, and then this basically becomes like you have like two arrays. One of them is array of values, one of them is array of difference, and then you want to build the segment tree on the array of difference. But the segment tree on array of difference is a GCD segment tree. So you want to be able to compute from L to R what's the GCD. And then so you have like several segment trees here, min, max, and then you want to find the this max as well, or the min of this as well. Many segment trees. Exactly. Like okay. There's a hash solution. Like of course, like once you found what's the minimum and the maximum, you can get the difference. But then, how do we actually check whether? So we know what's the minimum, we know what's the maximum, but how do we check actually like the dots are be apart and not like other? If you just take the sum, it's not correct, right? Like it might be one adjusted to the left here and one adjusted to the right, and if you take the sum, it's correct. Like the sum matches, but it's actually not an arithmetic progression. So I specifically created a test case of this, but if you take the square, you'll get correct. So if you take the sum of square, so you know what should be the value of this, right? Using some formula basically. And then if you also have sum of squares in your segment tree, so you can query the sum of squares of in a range. You will get easy. I did not create a test case that kills that. So or any kind of other hashing, right? If you become clever, Of course, if I create this test case, then you can come up with 8 cubes, sum of cubes, they'll never stop. So I decided to just stop at like the linear sum. But yeah, if you try to do any like more clever, then you'll get easy as well. Okay. Yeah, so that's problem J. Next is problem B, forbidden card.
So in this problem, there's basically a game in which there are n players, and they each have 2 cards. And the cards have an order. So they have an A card that's different to a B card, and they always try to play their A card first. So in this hypothetical game, there's some rules, and if it is their turn and they're gonna play, and this card's gonna play it, they play it. They don't even consider the second one. And the rules of the game is that if someone already played a 1, you can't play a card that has a 1. And each card has 1 number on it, and there can be several players with the same card, of course, because if not, the rules wouldn't make any sense. So the question is not just in a regular game. There is like a dungeon master that can say, card number 5 is forbidden. So it's basically as if before the game starts, this card was already played. So one key observation is that, let's say this is the set of cards. So we can simulate like the normal game without the dungeon master intervening. So he plays this one, he plays this one. Let's do a 4, 8 here. He plays this one, he plays this one, and he plays this one because he couldn't play the 4. So if we forbid a card, let's say we forbid 2, in each step, the set of forbidden cards only increases. It might be the same or it increases. I think it always increases actually. So in this case, the only sequence of affected moves was the first person, the only person that played that card. So in this case, this person would play this card. So let's say someone down here in the regular game had played number 3. So then, like this sequence of events would trigger him or her to change his move or their move. So it starts being like a jumping game, but we know that at some point, let's say someone here has 2, 4, they're gonna lose. Like this person lost in the regular game, either in the first round or in the second round. We can simulate that. We can go up to the beginning of the 3rd round, because if everyone has different cards, the loser is the first player, because he's the one that's gonna run out of cards first, and it's his turn. So even if we restrict this, we're never gonna go past this point, because like we mentioned, the forbidden set would only increase in size. So if he couldn't play before, he definitely can't play it. So what we can do is, for each of these hops, you can just DP over it. So I say, what happens if this person has a change? It would always be the sequence of events, and also like this. So to avoid doing it over and over again, we can do it as a repeat. It's basically all fun. And then we can actually iterate over all possible forbidden values. And for each of them, since we like recompute the P, we can know of 1 who's the last player that's affected. If no one in this sequence loses because of the change, the original person loses. If, let's say, the other option this player had was a 4, so when he can't play that 3, he doesn't have any options, so he loses. Those are the 2 options. Either someone in this sequence of events is the new loser, or the original loser is still the loser. And we can like pre-compute the turns, and with the turns it's enough to know when someone doesn't have an option. You can just pre-compute also in which turn each card was used. So in this point, if you know that this card was used before, that's enough. You don't have to like have a set or anything to keep tabs on the cards that have been played. You can just use the first simulation as the source of information for everything. So in the end, it's basically an O of M, because M is the number of forbidden cards. And DDP is like O of N, because N, it depends on the number of turns. But in the end, like it's linear, and yeah, that's basically the key observation of the set. The forbidden set, it's like someone played before, so the forbidden set only increases. Any questions?
So yeah, this problem basically like just figure out what's the chain of events that happen if X is forbidden. And yeah, the idea is correct. Like first you simulate the game if there is no forbidden card. My solution is a bit different too. Yeah, it's essentially the same, but easier to illustrate. I illustrate it in different ways. So when we simulate this, let's say this is the card that is chosen, and here is 8, here is 3, 12, it is okay, here closes, yeah. Yeah, so for my solution, we build a graph, something like if the nodes are the card index, and whenever we run this simulation, if we choose the first card and the second card is not chosen, we add an edge. So in this case, because we chose the first card and the second card is also can be chosen, we add an edge. This means that if this is forbidden or this has been used before, this will be forbidden as well, right? This will be used as well. And then here 2 to 3, we add an edge, and then 4 to 5, we add an edge, and then yeah, here we don't add an edge because one is actually have already been used before, so we don't add an edge, and then so on, right? And then this one we also don't add an edge because it's actually already the second card that we play, right? 3, 4 we also don't add an edge, 12, 13, and then so on, right? And then we also, for each of these nodes, we also keep track which player is playing that card. So in this case, this is the first player, this is the second player, this is the 1, 2, 3, 4, 5, 6, sixth player. 4 is third player. 5th is none. It's not played. There can be cards that are not played. 12 is played by the 7th player, and this is not played by anyone, right? Okay, and then yeah, for let's say this 2 is forbidden, then we just want to find who actually played the third card. Also the same is 1, who actually played the third card. So for each node we can pre-process to find who is the end. Like if you traverse this graph, because this graph will each node will only have 1 degree. There can be many out in degree, but it will only have 1 out degree. We traverse, so for each node we traverse to the end. Yeah, of course we can optimize this if you already know what the end of this. When this reaches this, we just also yeah, that's the dB. Where the dB? Yeah, you can say it's a dB. Yeah. Yeah, or you can. Yeah, and then if this is at the end of, so if 1 is forbidden, this is the end of the traversal, and the 6th player will lose that. Yeah, because first player will actually play this, second player will actually play this, and the 6th player don't have any choice, right? And then if let's say 4 is forbidden, the end of this actually is not played by anyone. So the loser of the game, if we forbid 4, will be the original loser of the game, which is this player, right? Yeah. So that's how we can. So yeah, in linear time, all in linear time. Okay. Next, okay, there's only one solver for this problem. Any volunteer for red black ball problem? Any takers? Who solved this? And
If I'm not mistaken, it was F0 which is not participating.
it's not here. Oh, okay, that's right. Okay. Okay, so any of you want to try? Oh, okay. Okay, so yeah, the problem is but yeah, you can just try.
Okay, so in the problem, you had like colored balls of 2 color, black and red, I think, and then there were uncolored balls. So initially some colored balls. You have to put the uncolored balls in some order. And what happens